So in chapter number 4, CCENT, we are going to talk about layer 2, the data link layer. We're going to talk about how switches work. We're going to talk about how bridges work. We're also going to talk about different protocols that are used by switches and bridges to facilitate frame forwarding. Remember, a frame is a layer 2 concept. We won't get into the WAN protocols so much in this layer. Remember, a lot of our WAN protocols are also layer 2. Our wide area networking protocols like PPP, frame relay, ATM, those are all layer 2 protocols, but we won't quite get into that. We're going to talk about CSMA-CD. We're going to talk about ARP. We're going to talk about lots of things in this particular section. Okay? As we know, the data link layer is layer number 2. It is the physical layer, right? Slightly different than what you guys have on your diagram. All right? The physical layer. All right? Physical addressing occurs at this layer. We call that MAC addressing, at least with Ethernet anyway. All right? So we're talking about layer 2 of the OSI model. All right? Now there are essentially, there are a lot of different specifications at this layer, a lot of different protocols that function at this layer. But from an Ethernet standpoint, because that's what our focus is in this section, is primarily on Ethernet. From an Ethernet standpoint, there are 2 types of Ethernet that exist at this layer. There is Ethernet 2, right here, and then there is 802.3 Ethernet. I want to be very clear that these are completely different types of Ethernet. Ethernet 2 is the original form of Ethernet, and it was developed way back in the day. Well, actually, it was spearheaded by a company called Xerox, believe it or not. Xerox invented Ethernet. Well, primarily, right? Now, they did get in bed with 2 other companies, Digital Corporation and IBM, and they formed their own company called DIX, D-I-X. Stands for Digital Corporation, IBM, and Xerox. And they defined how Ethernet was going to work in the world. Now, there were other companies that were trying to develop their own form of Ethernet, and none of them really took off. In fact, IBM even tried to develop its own form of Ethernet called Token Ring, but it didn't really take off as a standard. All right? Now, the reason why I'm defining this is because 802.3 Ethernet is slightly different than Ethernet 2. 802.3 Ethernet is that form of Ethernet that has sublayers, the LLC and the MAC sublayer. Okay? Now, we'll talk about what those sublayers are a little bit later on. But let me make it clear that Ethernet 2 does not have those sublayers. Frame relay does not have those sublayers. ATM does not have those sublayers. Those sublayers are specific to 802.3 Ethernet. You can also see there are some other layer 2 specifications, token ring or 802.5, Wi-Fi or 802.11, Bluetooth 802.15.1 or other types of Bluetooth, WiMAX, which is broadband wireless in the registered spectrums, 802.16 and so on. So there are many, many different types of variations of Ethernet or variations of communicating over layer 2. Now, our focus is primarily on Ethernet 2 and 802.3 Ethernet. This snap header that you see here, let me find my mouse here. There it is. This is called a snap header. And it's called a snap header because it gets added on top of Ethernet to perform a specific function. Now, I'll show you what that function is a little bit later on. We've got to make sure that everybody's muted. We got somebody joined that's not muted here. Okay. All right. Now we'll talk about what that snap header does a little bit later on. But again, 802.2, that is not something you're going to see in Ethernet 2. And you can kind of see what it is. Ethernet 2 kind of goes all the way across the physical layer and data link layer Whereas all these other IEEE functions, they have a physical layer component, they have a MAC sublayer component, but all these other IEEE specifications of Ethernet use 802.2 to perform the LLC function. Does that make sense? So this 802.2 function is effectively the logical link control sublayer. That's why it's kind of mapped across here. All right? So we'll see that as we progress through the section here. I guess then what is the question? The question is, well, what Ethernet do we use today? If I was to open up Wireshark and start capturing frames from my PC, what is it going to be? Well, guess what? It's going to be Ethernet 2. It's going to be Ethernet 2. All right? 90% of all devices, Windows, Linux, Macintosh, they all use Ethernet 2. Cisco uses 802.3 Ethernet for switch-to-switch communications, and you know, you can use 802.3 for other things, but primarily it's going to be Ethernet 2. Regardless of the protocol, however, regardless of the protocol, all right, at layer 2 we see a common format. We have a header, we have the data or the payload, and we have a footer. We see this in ATM, we see this in wireless, we see this in Ethernet, we see this in frame relay. Any protocol that functions at layer 2 is going to perform this kind of function, this encapsulation process. The header does vary depending on the layer 2 protocol, and we'll look at some of the common characteristics of a header in a little bit. But the footer, in every single case, even though it might be different sizes, the footer is the same. It performs the same function in ATM as it does in frame relay, as it does in X25, as it does in Ethernet. All right? We'll get into that in a little bit here. We have a question online. Where did the standard originally, were all the standards originally defined in 1980? No. The 802 came from the fact that the consortium or the group was established in February of 1980, but we still see standards today, like 802.11ac, which is one of the latest wireless standards, right? That was only ratified as a standard a few years ago, but it still starts with 802. 802 does not mean a standard defined in the 80s. It simply means it's associated to the group that was established in the 80s. Make sense? All right. Now you will notice one thing that's important when it comes to a frame, and it is this right here. Frame start. Oops, my pen's not working. Frame start, frame stop. Okay? These are called delimiters. Delimiters. And delimiters allow us to define the beginning and the end of a frame. Now, why would it be particularly important for us to identify when a frame begins and when a frame ends? If you were to open up Wireshark on your laptop and start doing a capture, you would see that essentially it is a constant flow of data, a constant stream of data flowing through that device. You know, you don't just get a frame here and then 10 seconds later get another frame and 10 seconds later get another frame. You're constantly receiving ones and zeros. Well, the other issue is that the packet, the payload, is variable in length. It doesn't have to be fixed. Sometimes it's 50 bytes, sometimes it's 1,000 bytes, sometimes it's 1,500 bytes. So in order to be able to differentiate between frame 1 and frame 2 and frame 3, every frame has that delimiting sequence of numbers and the frame stop component, which is a delimiting sequence of numbers, to identify the beginning and the end of a frame. When you're doing a Wireshark capture, you won't see those delimitations. Those are not actually captured. Those are carried from host to host on the wire. So it's a wire side function, right? It's not something, it doesn't actually represent actual data. All right? So let's get into a little bit about Ethernet. Early versions of Ethernet, obviously designed to operate in very slow environments, relatively slow to what we see today, about 10 megabits per second. Now we're operating in the gigabits per second range, but in reality, the same Ethernet we used before is the same Ethernet we use today. On the top, you see your Ethernet 2 frame. On the bottom, you see your 802.3 frame. All right? So what's common between these? Well, they both have 8 bytes of preamble. Right? Preamble is that start of frame function. In other words, the preamble does not represent any actual data. It's just the beginning of the frame. You'll also notice that the next section of the Ethernet frame is the destination MAC address, and that's common to both. 6 bytes or 48 bits. Destination MAC address. Now, there's a reason why that field is first, because switches use that field to make a forwarding decision. And obviously, you want that switch to be able to make a decision as quickly as possible. Switching needs to happen at near wire speeds. So in order to do that, we have to process that frame as quickly as possible. The fact that the destination MAC address is the first real piece of data in the frame header makes that possible. We can do something called cut-through switching, where we simply start forwarding a frame before we're even done processing the rest of the data. The next field is the source MAC address in both formats. And then we see a little bit of a variation. We have a 2-byte type field, or we have a 2-byte length field. All right? Now, we'll talk about what that type field does in a minute. I don't want to talk about it right now, because then we won't have anything to talk about when we get to the next few slides. But the type field is very, very important. Then we have our data field, which is a variable length field, 46 bytes up to 1,500 bytes. All right? At a minimum, it has to contain 46 bytes of information. At a maximum, 1,500 bytes of information. That is based on our MTU, maximum transmission unit length. And then the last field we have is something called our frame check sequence. Again, something that we'll talk about a little bit later on. But let's just say that this is the error detection piece in Ethernet. The frame check sequence is how we identify whether or not the frame format is correct. All right? Well, here we go. On the top, we see an Ethernet 2 frame in Wireshark. On the bottom, we see an 802.3 frame. All right? Now, this will be the last thing we talk about on this slide before we move into our lunch break, but I want to point out a few things here. All right? And we'll see more Wireshark captures as we move forward through the rest of the class. But I can tell this is an Ethernet 2 frame, well, quite frankly, because it tells me it's an Ethernet 2 frame. But there's another reason why I can tell that, and I'll show you in a second. I can tell that this is an 802.3 Ethernet frame, well, because it tells me it's an 802.3 Ethernet frame, but I can also tell because I see things like LLC. We don't see LLC in Ethernet 2. Remember the first field that I said in Wireshark, or in the frame? The destination MAC address. Notice that the MAC address is written in hexadecimal format, right? Now, Wireshark converts part of that MAC address to a name. We'll talk about that after the lunch break. And then you'll notice that we see the source MAC. But two things that are very important here. And this is common to any type of MAC address, or any MAC address. There are reserved bits. The 7th and the 8th bit, if you're talking about from the left to the right, the 7th and the 8th bit are reserved for very specific functions. These are called the LG and the IG bits. LG stands for local or global. Local or global. IG, individual or group. Local means that the MAC address has been modified from its globally assigned format and is locally significant, meaning that there may be a redundant or another MAC address that's the same somewhere else in the world. MAC addresses are unique throughout the world. They're assigned by the IANA, at least the vendor ID is assigned by the IANA. Well, after lunch, we'll talk about the breakup of the MAC address. But If the 7th bit is a 0, that means that this is most likely the burned-in address. It's the globally assigned address, and it's unique throughout the world. That's why it's called globally unique, meaning nobody else in the world has this MAC address. All right? So if you're modifying MAC addresses, which some applications allow you to change MAC addresses. I do that on my computer, right? You go to an airport, and the airport allows you 30 minutes of free internet access, and then after 30 minutes you have to pay for it. Well, I have an application on my computer that changes my MAC address so that I get more free time, right? All I do is change my MAC address and I get another 30 minutes. Because that's how they identify you by your MAC address, right? Now if they were smart, they'd write their application to look for that IG bit or LG bit to see if I've modified my MAC address or not, but they're not that smart. I also figured out, like on United, all right, like United Airlines, if you use a VPN proxy that listens on port 53, you get free internet. You don't have to pay for the internet because their proxy doesn't work. It looks for authentication on port 80. There's ways around all kinds of stuff, but being a smart network engineer sometimes has its benefits, right? All right, now the IG bit, individual or group, what do you think that means? Individual or group. Is this a unicast MAC address or is it a broadcast MAC address? Is this a unicast MAC address? Is it a multicast MAC address? Right? Let's see. How can I get the study materials? I will have to reach out to you a little bit later to talk about the study materials. All right? Defer that question to later. Anybody that's participating in the class, if they're participating for the week, I'll be reaching out to you to talk to you about how to get the study materials. Okay? So those bits are set to 0. They're set to 0 because this is a unique MAC address. It's not broadcast, it's not multicast. Now you'll notice for 802.3 Ethernet, everything kind of looks the same. Certainly the first part, destination MAC is here, except for there's a difference. This bit is a 1, meaning that this is a group address. This is the multicast MAC address used for spanning tree. All right? You'll also notice that we have something called LLC. If you remember, this is that 802.2 header. 802.2. Right? If you go back here, doesn't 802.2 correspond to the LLC sublayer? So that's what you're seeing here in this case. With 802.3 Ethernet, we have that 802.2 snap header. Okay? DSAP stands for Destination Service Access Point, and S stands for Source Service Access Point. And it basically allows us to identify the protocol. All right? Now, let me point something out here, because this is something I skipped over, the type field. Remember, that was a 2-byte field. A 2-byte field that allowed me to identify what? Well, what layer is IP? Layer 3. So the type field allows me to identify what's being encapsulated. In other words, what is the next layer that I have to send this data to? The next layer I send this data to is IP. Okay? That's what the type field is designed for. We have a question here. The slide is page 51 in the PDF, a little bit out of order. Sorry about that. Slightly out of order. We tend to modify our materials quite often, so sometimes they get a little bit out of sync. Okay. Oh, I thought it was a different one. It's actually 51. Yeah. And as I mentioned before, 802.3, we have 2 sublayers. We have the LLC. Primarily, the purpose of the LLC is to handle communication between the upper and the lower layers. Upper meaning layer 3, lower meaning layer 1. The MAC sublayer, data encapsulation as well as media access control, addressing, framing, converting signals from ones to zeros and so on, or bits, converting information within the frame to bits to transmit over the physical wire. Okay? So this will be a good place. We'll go ahead and pause here. I'm going to pause the recording since it is running into our lunchtime. So welcome back from lunch. We left off on this slide. We were talking about LLC and the MAC sublayer. MAC sublayer, that's the lower half of 802.3, right? The LLC is the upper half of the LLC, of the 802.3. The MAC sublayer is the lower half. It's responsible for data encapsulation, meaning that it takes that frame information, it converts it or encodes it into an appropriate format, and it sends it over the physical layer in the form of ones and zeros. In addition, the MAC sublayer is responsible for addressing, particularly in the form of MAC addresses, right? Also, frame delimitation. We talked about the concept of frame delimitation, the beginning and the end of the frame, the addressing component, and finally, what we call the frame check sequence, or the FCS. Within the FCS, we have something called a cyclic redundancy check. Now, here's how that essentially works. I build my entire frame, and before I encapsulate that data and send it over to the physical layer, I run a mathematical calculation called the cyclic redundancy check. It's an algorithm that I use to generate a number. And that CRC value is determined based on the amount of information that's stored in the frame specifically. I send my data to the destination. After the destination receives the frame information, it does the same mathematical calculation. If the numbers are the same, then that means what was sent is what was received. If the numbers are different, that means that the information that was sent somehow changed or was modified in transit. When I received the information, it wasn't the same. Does that make sense? So we get a CRC error. A CRC error means that the calculation failed. At that point, the frame gets dropped, and it's up to the upper layers then to identify whether or not the frame needs to be recreated and retransmitted or not. Layer 2 has no correction mechanisms. It only has detection, right? Now, as far as the frame size goes, we know that in Ethernet 2 and 802.3 Ethernet, we define a minimum size of 46 bytes and a maximum size of 1,500 bytes based on MTU. That excludes the frame header and the frame footer. Now, we already know that the frame footer is 4 bytes. The header is what? Well, 14 bytes. You got 6 bytes for destination MAC, you've got 6 bytes for source MAC, you've got 2 bytes for type field or length field. So all said and done, the header is 14 bytes, the footer is 4 bytes, giving us a total overhead for Ethernet of 18 bytes. We have a question online that says, is this a simplified hash? Yes, essentially it is a hashing function, a mathematical calculation to derive some sort of number. All right, and it's based on input values and output values, right? The input values being the frame information, the output being the hash itself. And that hash gets verified on the receiving side. Anything that's less than 64 bytes, which includes the header information, by the way, anything less than 64 bytes is considered a collision or a fragment. And generally speaking, most devices that are processing layer 2 will drop those frames. Anything over 1,500 bytes is considered a jumbo frame, right? Now, we can program devices in the network to allow for the transmission of these jumbo frames. or giant frames, or there's different terms that we would use to describe it, but anything over 1,500 bytes is irregular. Now, in certain types of networks, like storage area networks, we might actually use large frame formats so that we reduce the overhead and increase the amount of throughput that we can support with these layer 2 networks. So in storage area networks, it's actually kind of general practice to have these larger frame types, or frame sizes, excuse me. But typically in standard Ethernet, that's not the case. So we'll just do a quick review, kind of break this down a little bit. The preamble, used for synchronization, also containing a delimiter to mark the end of the timing information. There is nothing within this preamble or within the timing information that contains relevant information for forwarding data. It is simply a synchronization pattern. The destination MAC address, a 48-bit MAC address. The source MAC address, a 48-bit address. The type field. As I mentioned before, the type field allows us to identify the next protocol at the next layer. If it's IP, it's going to be hex 0800. If it's IPv6, 86DB. If it's ARP, 0806, and so on. Several different layer 3 protocols have types. The idea being is that whoever's processing this data, if they need to process the information at layer 3 or above, they know what the next process the data gets sent to is. For example, a router needs to know, okay, am I going to process this through my IPv6 control plane, or am I going to process this through my IPv4 control plane? And of course, the type field will allow us to identify that. Same thing for a host. Okay? The payload, that's my data field, anywhere from 46 to 1,500 bytes. If we don't have enough data in our data field, we can put in these things called padding bits. They're basically stuffing bits that we put into the field to make sure that we're meeting that minimum requirement. Make sense? And then we've got our frame check sequence. As I mentioned before, in Ethernet, that's a 4-byte field indicating that cyclic redundancy check, or that hash value that we put into that field to identify whether or not there's an error in the frame transmission. What's the most likely cause of issues when it comes to frames? What's the one thing that will probably cause or be the most common form of an issue when it comes to frames? It's going to be collisions, right? It'll be collisions. Collisions are what we have to try to avoid. Collisions cause framing errors. They cause frame drops and so on. All right? Now, conversely, if we were to look at this from a 802.3 perspective, we would see that it's pretty much the same. The only difference is instead of a type field, we have a length field, and instead of the data field just containing our raw data, it also has the 802.2 snap header. Now, what I've done here is I've put in some other framing types just to give you an idea of some of the differences. Here's a PPP frame. Well, guess what? We kind of see the same thing. We have a header, which is comprised of a flag field, an address field, a control field, and a protocol field. And we have a footer, which is comprised of our frame check sequence. Now, notice the flag field here is pretty much the same thing as the preamble. But instead of it being 8 bytes, it's only 1 byte. All right? Binary sequence of numbers, 01111110, to allow us to identify the beginning of our PPP frame. Okay? The address field, a single byte that contains a PPP broadcast address. Now, why don't we have unique MAC address identifiers in the point-to-point protocol? I know you guys don't know much about PPP right now. We'll learn all about PPP on Friday, but why do I not have to specify a source and destination address? Because it's point-to-point. By point-to-point protocol deals with hosts that are point-to-point, meaning that the source can only be one device. the device on the other side of the link. The destination can only be one device. The device is on the other side of the link. You follow me? All right. So the PPP protocol doesn't have to identify a source and destination MAC address because there's only two devices communicating on the link. All right. So there really is no addressing component in this case. It's basically what it boils down to. HDLC does the same thing. SDLC does the same thing. Frame relay is slightly different because in frame relay, we can do point-to-point implementations or we can do point-to-multipoint implementations. So with frame relay, we might have to concern ourselves with addressing. Addressing in frame relay is done with a special address type called a DELC, a data link connection identifier. We've got a control field that contains a binary sequence. Basically, that doesn't change. We know what the protocol field does already. That allows us to identify our upper layer protocol. That's in hexadecimal format. And then we've got our data field. All right. Now notice the data field here doesn't really specify a minimum and maximum. And that's what I meant by MTU sizes will vary. Framing formats might vary or sizes might vary depending on the protocol. Different layer 2 protocols have different requirements for sending and receiving data or encapsulating data into that data field. All right? And then our frame check sequence. Now in this particular case, with PPP, we can use a 2-byte CRC or we can use a 4-byte CRC. One has a parity component, the other one does not. Normally, it's just simply going to be 2 bytes, which is 16 bits. All right. The fidelity of the calculation can be enhanced by using the 4 bytes, but typically you're going to see an implementation with 2 bytes. Now, you're not going to have to know the frame format on the test. They're not going to ask you to identify the fields of a PPP frame header or an Ethernet frame header, but this is a design class, this is an engineering class, and our goal by the end of this class is for you guys to have a very clear picture of how these protocols are structured and how they function. These are the fundamentals of networking, right? Here we see an example of an 802.11 wireless frame, obviously a lot more complex than what we would typically see. I want to be clear, though, this is on the wireless side. This is not on the wired side. On the wired side, we know it's Ethernet, right? So it's probably just going to be an Ethernet 2 frame. So this is the kind of format that we would see for the frame on the wireless side, on the radio side. I'm not going to go through every component here, but there are a few things that I want to point out. First of all, you have your header, which is everything to the left. Secondly, you have your footer, everything to the right. And then you have your payload. So just like every other layer 2 protocol, our wireless data gets transported with a header and a footer at layer 2. We've got a control frame or component. We've got destination address, source address, receiver address, sequencing, transmitter address, because the access point is acting as an intermediary between the infrastructure, right? So the destination and source address might be the actual physical destination and source, but the receiver and transmitter address might be components of the access point itself. All right? Even when we're running Ethernet with VLANs, we have a special framing type. We're going to be talking about VLANs in a couple of days, but when you're doing VLAN tagging, even the standard Ethernet frame gets modified. We insert this 4-byte tag. It's called a shim because it gets inserted. We don't actually change the format of the original frame. We just simply insert this tag in between. Now, I won't get into a lot of details on what this tag looks like right now. We're going to see this exact slide again later on when we get to the VLAN section, okay? But that tag allows us to identify what VLAN that frame belongs to. There's a few other components, a new ether type, for example, a priority field used for class of service, a conical format identifier, what they call here the token ring encapsulation flag, which is not used for anything, and so on. Okay? One of the most important things that you can learn about a frame, though, about layer 2, is that layer 2 information never, ever goes through a router. Routers operate at what layer? Layer 3. Frames are layer 2. So anytime data goes through a router, the frame information is always stripped off and then reconstructed. So on the ingress, we have information. If you look at the diagram here, we've got a host that's communicating to the router over a wireless radio wave, right? So that's going to be encapsulated. That information is going to be encapsulated into a Wi-Fi frame. Once that data reaches this interface, all right, once that data reaches that interface, somebody's microphone is on. I'm trying to figure out who it is. Hold on 1 second. Usually it'll show me a little icon. Somebody is definitely transmitting. Huh, it's weird. Every time I stop talking, I can hear some static noise in the background. I'm not sure why that is. It might be Alexander's video camera. For some reason, his video feed is showing through here. Let's just do view all. That should work. Okay. So as this data passes from the PC over to the router, we know that's coming in a wireless frame. Now, what happens is when the router receives that information, what the router is going to do is the router is going to say, okay, is this frame for me? All right? And it's typically going to identify that based on the MAC address. Is this frame for me? Think about it this way. Think about it this way. You go to the, let's say you have a couple of roommates that live with you at your house. You go to the mailbox, you open the mailbox, you get a bunch of letters from a bunch of people, and what is it that you're looking for in order to be able to identify what is yours? My name on the envelope. Your name on the envelope, right? Well, that's basically what a frame is to a router. The envelope is kind of irrelevant. It's what's contained inside the envelope that the router uses to make forwarding decisions, right? But in order to know whether or not I'm going to open the envelope, I need to look at the name on the envelope. We'll call that, in this case, a MAC address. All right? Now, once you've opened the envelope, you don't care about the envelope anymore. You care about the contents of the envelope. So the envelope gets thrown away. All right? Well, think of that like a frame. Every time a frame enters a router, that frame gets stripped off, that header, that layer 2 header gets stripped off. Now, once the router decides, oh, okay, I've looked at the contents, I've decided I need to send that data to this router, what has to happen to that data? It needs to be put back into another envelope. But the envelope that's used on this link is different than the envelope that was used on the first link, because this happens to be a PPP link. So we're going to put the data into a PPP envelope, send it on its way. Same thing happens. This router receives that envelope and says, is this for me? Well, because it's PPP, it assumes it is, because I'm the only other person on the point-to-point link. What is the router going to do with the envelope at this point? Going to send it to them. Well, it's going to open the envelope. It's going to throw away that original PPP envelope. It looks at the contents of the envelope, which in this case is IP, and it decides it wants to send the information to this router, right? You want to send the information to that router. But now this is an HDLC link, so I put the data inside of an HDLC envelope. You get the idea. Every single time data passes through a router, layer 2 information gets stripped off and thrown away on the ingress, and then on the egress, that layer 2 information gets added back. Does that make sense?
Yeah, it makes sense. I just have a question. So the HDLC and the TCP and the frame routing, they are all different protocols?
Those are all different layer 2 protocols. Okay? Those are all different layer 2 protocols. Absolutely. ID is just what's being carried inside those envelopes. All right? The golden rule, every single time I go through a router, that envelope gets stripped off, and when the data gets forwarded out of another interface, the envelope gets re-added. It might be the same kind of envelope. If I go from Ethernet to Ethernet, I still strip off the envelope and I still add it back. Okay? Now we're going to go through a process a little bit later on called the packet delivery process, where we learn about what happens to the addressing of the envelope when that happens. All right? Which will also allow us to define the scope of Ethernet, layer 2 Ethernet. All right. Back in the day, we used to interconnect our networks using hubs. That's how it all started. Or we would connect the computers together on a bus. In fact, one of the earlier types of networks was something called 10-base-2, where actually all the computers were physically connected to each other with a coax cable. There wasn't even a device that allowed us to interconnect those computers. They were literally connected to each other with a cable. All right? Here's the problem, though. If those devices wanted to communicate, they could not communicate at the same time, because if two hosts tried to communicate at the same time, it would cause a collision, meaning that the data would get corrupted. Now, we don't see this too much in modern networks today because everything is collisionless, right? Every interface on a switch is a separate collision domain, and the interfaces are full duplex, which means we shouldn't really technically see collisions. But back in the day, we had something called contention-based network access, where you had hosts that were competing for bandwidth, competing for network access. We called that CSMA-CD, carrier sense, multiple access with collision detection. Carrier sense, multiple access with collision detection. All right? Stations could transmit at the same time, but if they did, it would cause a collision. So there had to be a mechanism in place to prevent that from happening, because every time there was a collision, data got corrupted and we would have to retransmit it. All right? Now, we don't concern ourselves so much with CSMA-CD today in modern networks. If your network is micro-segmented, in other words, you're using switches instead of hubs, then collisions are not something you typically concern yourself with. But back in the day, we did. And here's what CSMA-CD stands for. Carrier sense, multiple access with collision detection. Let's talk about the first part, carrier sense. Carrier sense means that each one of these hosts that were attached to this network, and by the way, it looks like just a wire, but it could be a hub. But each one of those hosts attached to the network would try to avoid collisions by not transmitting when somebody else is transmitting. It's kind of like we try to avoid a collision of communication in here. If I'm talking, you're not going to try and talk at the same time, and you're not going to try and talk at the same time. You're using your ears to identify that somebody is communicating, and you're making a logical decision, okay, I'm not going to talk if he's talking, because then we'll understand each other. Well, that's what carrier sense is. The computers are attached to the network. They're monitoring their network interface card for activity. Okay, now how are they able to do that? Well, in a hubbed environment, when traffic went into one port, what happened to it?
I don't know the others.
It gets duplicated out of every other port on the same device. So even if it wasn't meant for me, I would still receive it. Make sense? We don't see that with a switch, at least not if the network is efficient. We'll talk about where we might see that with a switch a little bit later on. So the idea is these devices are kind of monitoring the link, and they're saying, okay, if I'm host D, if B is transmitting, I'm obviously not going to transmit because I know that'll cause a collision. Multiple access simply means that we have multiple hosts that can talk on the network at the same time. All right? Now, a collision, we already know what a collision is. If two hosts try to transmit at the same time, we'll get a collision. All right? We'll get a collision, which means essentially that the data gets corrupted. Does that make sense? The data gets corrupted, but that brings in the last and final piece, which is collision detection. The devices on the wire are smart enough to identify when a collision occurs. Now, think about this. If you and I are talking, and I talk and you talk at the same time, what is our collision detection feature? You hear me talking, I hear you talking, and what do people typically do? They say, oh, okay, hold on. Go ahead, right? Or, you know, everybody will stop talking, and then we'll have an idea of who should start talking because of an algorithm. Well, that's what happens on the network. We have this collision detection feature that says, oh, there was a collision, everybody stop talking. Everybody start a random timer. And whoever's timer expires first, you can talk. Everybody else has to wait. That's called a back-off algorithm. It's basically just a stopwatch. It's a random stopwatch, so whoever caused the collision may or may not be able to transmit first. It just depends on what the timers end up being. The idea with this, though, is that if a collision occurred, that everybody stops talking, and then they all start their own random timer, countdown timer. Whoever's timer expires first, they're the ones that are going to be able to transmit. All right, meaning that hopefully a collision is not occurring now because everybody else's timer is still going. Make sense? Here's the downside to this approach, though. When a collision does occur, the network shuts down. Right? Now, it's milliseconds. It's not seconds or minutes, but the network shuts down, which means that every time a collision occurs, or the more often a collision occurs, the slower the network becomes, which is not a good thing, obviously. We also talked about the concept of a layer 2 address, right? We know for a fact, for example, in Ethernet, we use MAC addresses to define our destination. But why is it necessary to have a MAC address in Ethernet, but not have a MAC address in point-to-point? Well, because in Ethernet, we can have multiple sources and multiple destinations connected to the same segment, right? Host A, host B, host C, host D, host E, anybody could be communicating. So if A is talking to D in this particular network, right? A is talking to D, well, they're all connected to the same switch. So that means that potentially A could talk to C, A could talk to E, and so on. So we have to identify specifically who the source is and who the destination is. But in a point-to-point link, the source is the person on the left, and the destination is the person on the right. There may be a cloud in between, but logically speaking, this is a point-to-point connection. The cloud is like a service provider network. So if this is logically point-to-point, there's only one place the traffic can come from. It's the person on the left, and there's only one place the traffic can go to. It's the person on the right. All right? So with point-to-point type of protocols, you're not going to see addressing defined. We're just going to have a standard broadcast address that every PPP device listens to or every HDLC device listens to. We don't identify sources and destinations with their MAC address. All right? Now let's get into a bit of a discussion here about, I'm just going to open up Notepad real quick. Let's get into a bit of a discussion about MAC addresses, a little more detail. All right? This is a great discussion because it kind of goes into our discussion that we're going to have tomorrow about subnetting and everything else. But we already know MAC addresses are 48 bits in length. All right? 12 hexadecimal characters or 6 bytes. Now, we throw these numbers out. Mathematically, it might not make sense. Why is it 6 bytes? Why is it 48 bits? Why is it 12 hexadecimal characters and not 48 or 6, right? Well, it depends. It has to do with how hexadecimal numbers are represented. And we're going to go through a whole discussion about that. MAC addresses are divided essentially into 2 parts. Technically speaking, 3 parts, really. Well, I guess you could even say 4 parts. If you take the LG bit and LG bit and the IG bit, then you could potentially say 4 parts. But essentially, a MAC address is broken up into 2 halves. The first 24 bits are reserved for something called the OUI, the Organizational Unique Identifier. This is assigned by whom?
Manufacturer?
No, the IANA, Internet Assignment for Internet Authority for Numbers Assignment. Those guys are responsible for assigning OUIs. The manufacturer is responsible for assigning the last 24 bits, which is generally going to be based on something like a serial number, something that would be unique. The idea being that every single MAC address is globally unique, almost like a fingerprint. What extent does a MAC address technically have to be unique? To what extent does a MAC address have to be unique? Does my MAC address, does it matter if I have the same MAC address as a host in Japan?
No.
No? You got to say that with confidence, right? No. The answer is no. Because MAC addresses never go through a router.
So it's going to be, that's internal network.
Inside the LAN, MAC addresses have to be unique. They don't have to be unique beyond the router. We don't use MAC addresses to route information. We use IP addresses. So technically, even though MAC addresses are globally unique based on how they're assigned, they don't really technically have to be globally unique. But you have to understand where this came from. When routing didn't exist and all that existed was switching and bridging, MAC addresses had to be unique, right? In the 80s, the early, mid to late 80s, early 90s, we didn't have routing architectures. We only had switching and bridging architectures. And in some cases, only hubbed architectures. So MAC addresses absolutely had to be unique. But in modern networks today, the extent that a MAC address has to be unique is only up to the nearest router. You can have a host with the same MAC address on subnet A, talk to another host with the same MAC address on subnet B, and their only differentiation is that they're separated by a router. Shouldn't be a problem, okay? Needless to say, though, MAC addresses are globally unique because the IANA assigns OUIs to vendors, and you can go out to Google and search on OUI list or vendor codes, and you can get a database of all the vendors. Cisco presently has the most number of MAC address OUIs assigned, and it's not that many. You would think that they would have many, many more, but they only have, well, they have less than 2,000, right? OUIs. But if you consider how many MAC addresses can exist per OUI, that's a lot of devices. It's 2 to the power of 24 per OUI, because there's 24 bits reserved for the vendor code. All right, so what you're seeing on the right side here, we've already talked about. This is the 6th octet. This is the 1st octet. So we know that a MAC address is 6 bytes. A byte is called an octet because it's 8 bits long. We also know that within the OUI, we have bit number 2 and bit number 1 reserved for the UG and LG bits. Unicast or multicast, that is the IG bit, sorry, that's what I meant to say, IG bit, and globally or locally, that's the LG bit. Okay, we talked about that already. In order to understand MAC addresses, though, you have to understand hexadecimal. And quite frankly, it is very important that you understand hexadecimal anyway, because IPv6 addresses are written in hexadecimal. A lot of the fields that you'll see in Wireshark are written in hexadecimal format. You guys are not going to have to deal with hexadecimal when you take your exam. But this isn't always about just taking the exam. This is about understanding fundamentally how computers communicate. And they communicate with hexadecimal numbers. Well, ultimately binary. But one way of representing addressing is using hex. Okay? Every hexadecimal character is 4 bits. Now that has a foundation in mathematics. Hexadecimal is a base 16 system. You can see the decimal equivalents in the first column here on the left, 0 through 15, represent every possible hexadecimal value. All right, 0 through 9, A through F. It's called hexadecimal because hexa is 16. This is a base 16 system, meaning that we only have 16 possible numbers. The decimal is called base 10. Binary, of course, is called base 2, because in binary we only have a 0 and a 1. So then the question gets posed, well, why 4 bits? Why can't I represent hexadecimal numbers with 3 bits? Why can't I represent a hexadecimal value with 6 bits? Well, it's because of the way the binary math works. And this is a precursor, this discussion. I'm going to go into this in quite a bit of detail, but this is a precursor to our entire subnetting discussion, which is going to happen tomorrow. Okay? When you're converting from decimal to binary and vice versa, we use something called a radix scale, R-A-D-I-X, a radix scale. Okay, and we'll see more about this tomorrow, but here is my radix scale. That radix scale always starts at 2 to the power of 0 on the least significant bit side, the right side. And then we increase the exponent by a factor of 1 for as many bits as we need to represent whatever number we're trying to represent. Now, on the decimal scale, take a look at the slide. On the decimal scale, what is the range of numbers to represent every hex character? On the decimal scale, it's 0 through 15. 0 through 15, right? You see that over here on the left, right? The decimal scale, 0 through 15. Okay? Well, I'm going to go into this in more detail, but let me just tell you real quickly, I only need 4 bits. This is bit number 0, this is bit number 1, bit number 2, and bit number 3. Sometimes they'll just say bit 1, 2, 3, and 4. I only need 4 bits to represent every possible decimal value from 0 to 15. And it has to do with how those numbers are calculated. All right? The second row that you see in this chart, this is the value in decimal of the corresponding column in binary. So 2 to the power of 3 is equal to a decimal 8. 2 to the power of 2 is equal to a decimal 4. 2 to the power of 1 is equal to a decimal 2. And 2 to the power of 0 is equal to 1. Okay? Any number factored in with an exponent of 0 is equal to 1. Okay? So, let's say that I wanted to represent 10, decimal 10 in binary. I would simply turn on the columns that add up to 10. Does that make sense? So 1010 is equal to 10 in decimal, which, by the way, corresponds to A in hex. There's no mathematical calculation to get from 10 in decimal to A in hex. It's just that's what it is, because we match up the corresponding letters and numbers in hex to the decimal numbers in decimal. All right? I'm kind of skirting around the whole discussion of binary to decimal conversion because, well, it's something that we talk about in a lot of detail when we get into the subnetting section, and I really don't want to overwhelm you guys with that right now, but you have to have a fundamental understanding of it to understand this hex conversion. All right? What if I wanted to represent 15 in decimal? What would the binary equivalent of 15 be? Well, it would be 8, right? So the 2 to the power of 3 bit would be turned on. It would be 4, that's 12, plus 2 is what? 8 plus 4 plus 2 is 14, plus 1 is 15. You guys follow what I'm saying? The decimal value, look at the black numbers in the bottom row. The decimal value of 8 added to the decimal value of 4, added to the decimal value of 2, added to the decimal value of 1 is equal to 15. So to write out 15 in binary, I would write it as 1, 1, 1, 1. I don't need any more bits because the maximum value I have in hex is F. If I had a G, let's say imaginary G, that corresponded to 16, then I would have to go to column number 5. Because I can only represent up to 15 with 4 columns. This will make more sense as we move forward. I promise you that. In fact, let's take a look at an example. All right, now I'm going to go through this very, very slowly because this is important. This is an extension of what we were just talking about. Numbers in computing generally are represented in 3 possible formats. Binary, which is a base 2 system, decimal, which is a base 10 system, and hexadecimal, which is a base 16 system. In hex, we have 16 possible values, 0 through 9, A through F. So you can see written there our base 16 scale. Our corresponding base 10 scale is just simply 0 through 15. So far, so good? All right. A binary scale is just the ones and zeros that we have to represent the hex or the decimal value with a string of those ones and zeros. Does that make sense? In other words, any hexadecimal number can be represented with a string of ones and zeros, and any decimal number can be represented with a string of ones and zeros. The larger the number, the larger the hex value, the larger the decimal value, the more ones and zeros you need. So if I want to represent 12 in binary, I only need 4 bits. If I want to represent 1,000,012 in binary, I need a lot more than 4 bits. Okay? Again, we have this scale called the radix scale. Now what I've drawn here is a larger radix scale. What we saw on the previous slide was only a 4-bit radix scale. Here we're seeing a 10-bit radix scale. This scale always starts at the power of 0. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on. As you add more bits, you simply add another exponent, or increment the exponent. All right? What do the blue numbers represent? Just below the scale. What do those blue numbers represent just below the scale?
The decimal value.
The decimal equivalent of that calculation. So 2 to the power of 9 equals 512. 2 to the power of 6 equals 64. You also notice there's a pattern, right? The next bit is always double the previous value. So 2 is double 1, 4 is double 2, 8 is double 4, 16 is double 8, and so on. You guys understand this concept that the larger numbers you're trying to represent require more bits. Because how do I write the binary equivalent to a large decimal number? I turn on the columns that add up to that number. If I wanted to represent 514 in binary, using that scale, 514 in binary, I would turn on this bit, I would turn off these bits, 0, 0, 0, 0, 0, 0, 0, 1, 0. So to represent any number, you just simply turn on the bits that add up to that number in decimal. So it makes sense to say the larger the decimal number, the more bits you need. Would I be able to write in binary 2048 using that scale? No, because I can't get above 1023. If I turned every one of those columns on, it would equal 1023. Little trick, guys. All the bits turned on is always one less than whatever the next column is. The next column is 1024. So all these bits turned on would be 1023. If you look at the 32, everything to the right of 32 turned on is 31. If you look at the 64, everything to the right of 64 turned on is 60. Okay? Now, since hex numbers only go from 0 to 15, then we only need 4 bits to represent every hex character. Because what is 8 plus 4 plus 2 plus 1? What does that equal? 15. That's right. It equals 15. I don't need any more bits. So every hexadecimal character is only 4 bits, period. All right? 0 in hex is 0 in decimal, which is 0, 0, 0, 0 in binary. F in hex is 15 in decimal, which is 1, 1, 1, 1 in binary. That make sense? But what happens when my hex character is not just a single digit? What happens if I said hex 86DD or hex 0806? Well, let's actually take a different approach. Let's go from decimal to hex to binary. So I have 1576 written in base 10 format. The subscript 10 there represents the base. So I have 1576 written in base 10 format. In other words, that's the decimal number. I want to give the equivalent value in hex and the equivalent value in binary. In order to calculate the hex value, we need to convert to binary first. Very important. Okay, now, in the reality, do we have calculators that do this in the real world? Of course we do. But you know what? You don't get a calculator on the test, first of all. And secondly, if you don't know how the math works, how are you going to know how calculations are done? How are you going to know fundamentally how protocols work? You have to understand the math in order to understand the logic. So this is not an exercise in learning the math. This is an exercise in understanding the logic. Very important concept. All right? So 1576, I know that I'm going to need 11 bits to represent 1576 because it's greater than 1023. Okay? So obviously the 1024 column is turned on, right? The 512 column is turned on, so I'm taking that number plus that number plus the 32 plus the 8, and that's going to equal my 1576. 1024 plus 512 plus 32 plus 8 equals 1576. All right, you guys agree with that? All right? The question is, and that's how simple it is to get from a decimal number to a binary number. It's no different if it's a larger decimal number, we just have more bits. What's the 12th bit value going to be? 2 to the power of 11. What's the 13th bit value going to be? 2 to the power of 12, and so on. Okay?
What is the 0x in front of the 628 represent?
Well, we'll get there.
Okay.
We'll get there. The question is, what does the 0x in front of the 628 represent? We'll get there. All right? But before we get there, how do I get from the binary value to the hex value? And this is why converting to binary is very important. From the right to the left, divide our binary strings into blocks of 4 bits and simply convert the value of those 4 bits to their decimal equivalent and then their corresponding hex equivalent. Now, it happens to be that 628 in base 10 is the same in hex, 628, because we don't have anything above 9. If it was 1028, then we would see an A instead of a 10 for the hex portion. So the question was, what is the 0x? That's a 0, not an O. What does the 0x represent? Well, it means that the number that follows is hex. Because if I just wrote 628, how would you know if that's decimal 628 or hex 628, right? So you'll see this often written in Cisco speak as 0x. There are other ways to write it. You can put a little h at the end of the number. You can, write hex if you want, but in Cisco, we always see the 0x. Let me go back here and show you what I'm talking about. Go all the way back to my Wireshark capture. Right there. Look at the type field. 0x 0800. Right? 0x means hex. So that is a 0800 in hex, which means it's 0000, 1000, 0000, 0000, if I was to convert that to binary. Because the first hex 0 is 4 zeros, the second hex 8 is 1000, and so on. You see what I'm saying? I'm talking specifically about this type field. This is binary of 4 zeros, that's binary of 4 zeros, that's binary of 4 zeros, that is a 1000. All right? I mean, think about it, guys. You're going to be looking at Wireshark captures. You're going to see that 0x You're going to know that that's hexadecimal, but now you know what that means in a binary string. All right? So that's what the 0x represents. Any questions? On the exam, you're not going to be required to do any hexadecimal conversions. You may be required to do some binary to decimal conversions, but no hexadecimal conversions. Within MAC addresses, we also have different ways of communicating. One of the ways of communicating is unicast. Very simple. The destination and the source MAC are globally unique, or they belong to an individual host. Just like with IP, unicast means one-to-one. Well, at layer 2, it's the same thing. It means one-to-one. Okay? Or we can communicate with broadcasts. There's only one broadcast address that exists at layer 2, and it's the all Fs address. Whenever you see all Fs, that means that this traffic gets flooded. Now, does that mean it goes to a router? No. In fact, even though it's broadcast at layer 2, doesn't mean it's broadcast at layer 3. In fact, in this case, it's unicast at layer 3, but broadcast at layer 2. Not oftentimes you see that, but it can happen. What does it mean for a layer 2 broadcast? What is the scope of a layer 2 broadcast? It goes everywhere within the subnet. Switches flood layer 2 broadcasts. Switches flood layer 2 broadcasts.
That's layer 2.
Layer 2. We're talking about a layer 2 address. We're talking about affecting layer 2 devices. Okay? We also have multicast at layer 2. All right? Now, in IPv4, the OUI for all multicast layer 2 traffic is 01005E. Every single every single IPv4 multicast frame starts with the same numbers, 01005E. All right? The last half is derived from the destination IP. This is a multicast destination IP address. This happens to be an all hosts multicast address. The last 23 bits of this address are used to derive the last 24 bits of the MAC address. You can kind of see a relationship there, right? 0.0.0.1 converted to hex 000001. Now, obviously, there's a commonality between those numbers. The number on the right is in decimal. The number on the left is in hex. But what do both of those numbers have in common? They both have some sort of binary representation. All right? So, we know what a MAC address is. We know what the format of a MAC address is. We already talked about the concept that MAC addresses are burned into a device. So they're generally kind of like the name of the device. All right? It's called a physical address because it's physically assigned to the device itself. It's either on a chip on the processor board, or it's burned into some sort of ROM or read-only component. IP addresses, on the other hand, more like a name. It's a logical representation of the host based on where the host is located. Now, in order for computers to communicate, both addresses need to be known. Even if the destination is not in the same subnet, MAC address plays a role. Even if the destination address is not in the same subnet. All right? Let me talk about that for a second, because we're going to talk about another concept which is extremely important when it comes to layer 2 communications and layer 3 communications in an IPv4 network. It's called the Address Resolution Protocol, or ARP. ARP, the Address Resolution Protocol. What is it for? Okay? Well, let's talk about, let me open up my notepad here. Let's say that PC1 wants to talk to PC2. All right? And it doesn't matter if they're in the same network or if they're in a different network. All right? And let's say, okay, we've got layer 2, we've got layer 3, and we've got layer 4 that we have to deal with. And let's say PC1 is just a Windows machine, and PC2 is a web server. All right? Within the header, we haven't looked at layer 4 headers or layer 3 headers, but within the header, we know that we have a source MAC, and we know we have a destination MAC that has to be filled in. Within the layer 3 header, I know that there is a source IP and a destination IP. And in a layer 4 header, there is a source port and there's a destination port. Okay, again, we haven't seen layer 3 or layer 4 yet, but I'm telling you that that's what's there. These are the addressing components for communicating across the stack. PC1 is sending information to PC2. Do I know what the source MAC address is of that data? It's me, right? PC1. You guys agree with that? Do I know what the source IP address is of the data?
Yes.
Sure, it's PC1's IP. Do I know what the source port is? Well, I'm going to tell you the answer is yes, because it's a randomly generated port that I generate myself. It's called an ephemeral port. So we'll just call that TCP 3161. That would be a port that I would just randomly generate on my own. Do I know what the destination port is? Well, yes, because it's web traffic. Again, we haven't talked about layer 4 yet, but I know that it's HTTP, which uses port 80. Do I know what the destination IP is? Well, let me see. What did I do? I opened up a browser and I put the address into the URL field.
The DNS will switch this, whatever, google.com to
IP.
IP.
Right.
Yeah.
So I know the destination IP because I put it in.
Mm-hmm.
All right, so that is PC2 IP. But here is where we get to the point that information is not known. What is the destination MAC address? I've never talked to this web server before. I don't know what the destination MAC is. Okay? Now, I could put in here all Fs, which is a broadcast, right? And sure enough, that frame would go out, it would hit the switch. What would happen? The frame would get flooded. Eventually, it would get to the router or the other PC, and it would get to its destination. By putting in an address of all Fs, though, I've essentially made my switch a hub, because the switch floods everything. We haven't talked about that either. The MAC address, Scott Ferris online said, the MAC address of the destination router inside interface to the network that is known. Yes, well, we'll get there. He's correct, assuming that the web server is not in the same subnet. Okay? But that's more specific than what I'm trying to get to here. What I'm trying to point out is that the destination MAC address is something that is unknown. It is something that needs to be discovered. Because if I don't know the destination MAC, like I said, I could put in all Fs, but then that makes my network very, very inefficient. All right? So I need to fill in that field. Well, the protocol that we use to do that is ARP. The address resolution protocol allows us to discover the MAC address that the frame needs to be sent to. Okay? based on already knowing what the IP is. All right? But there are two things that can happen. If the destination host that I'm communicating to is in the same subnet, then the ARP request will simply go to that host, and I will try to learn the MAC address of that particular device. Okay? Now, how do I know whether or not the destination is in the same subnet? Because I know the source IP, I know the destination IP. I know what my subnet mask is because it's configured on my host, so I can do some basic math and say, oh, the destination IP is in the same subnet, or it's not in the same subnet based on a calculation. If the destination host is in the same subnet, I send out the ARP request with that particular destination in mind. Now, in a minute, we're going to see what an ARP request looks like in Wireshark. It's not what you would expect, all right?
So I'm sorry, if it's not within the same subnet, what will happen?
If it's not in the same subnet, hey, how about that? I have a diagram that shows that. If it's not in the same subnet, there is no way for my PC to ever discover the MAC address of the destination. Okay? Because, number one, ARP requests are broadcasts. Routers don't forward broadcasts. So I can never send an ARP through a router. But number two, at what point does layer 2 matter, and at what point does layer 2 not matter? Layer 2 matters up to the router. Routers are layer 3. So anything behind that router has to be routed, not switched. Meaning that the MAC address is only relevant to that router interface. So, in the event that the destination is outside of my subnet, I don't try to discover the MAC address of the destination. Nope. I try to discover the MAC address of my gateway, which is the router interface. All right? We'll see more about that when we get into the packet delivery process. But layer 2 never goes to a router. So the source MAC of the frame, in this case, would be 1111. The destination MAC of the frame would be 3333. The source IP would be 101. The destination IP would be 22. All right? That's the address resolution protocol process. Now, what does that look like in Wireshark? Well, first of all, ARPs are broadcast at layer 2. Okay? This is important because when a switch receives an ARP request, it floods it. All right? The other thing that's important to understand, look at the type field for ARP. The type field is 0806, which means that ARP is its own layer 3 protocol. It is not carried inside of IP. It is literally its own layer 3 protocol. All right? This is an ARP request. I'm trying to discover an Ethernet MAC address. That's the hardware type. Hardware meaning the hardware address. The protocol is IP. It could be IPv6, but ARP doesn't exist in IPv6. Well, we probably had ARP with like CLNS or maybe IPX. I don't know if ARP existed in IPX or not. What about the hardware size? What does the hardware size represent? The number of bytes. That makes sense, doesn't it? If I'm trying to discover a MAC address, it's 6 bytes. What about the protocol size? Well, it's IP. IPv4 is 4 bytes, 32 bits. So I'm trying to resolve a 6-byte hardware address knowing the 4-byte IP address. Okay? The opcode, meaning what type. Is this a response, or is it request, and so on. Opcode of 1 means that it's a request. Opcode of 2 means that it's a reply. All right? But here is the most important part. The actual payload of ARP. The sender's MAC address is identified. The sender's IP address is identified. The target MAC is blank because that's what I'm trying to discover. The target IP is identified. Why is this particularly important? It's important because the only host that's supposed to respond to the request is whoever the target IP is for. Because remember, this is a broadcast, which means everybody gets this request. But the only host that's supposed to respond is the target IP. Now, ARP is inherently vulnerable to security attacks. Well, they're vulnerable to attacks. ARP spoofing attacks, ARP poisoning attacks, and so on. Because it's broadcast-based, it's not really that secure. So we use protocols like or methods like dynamic ARP inspection, DHCP snooping, and so on. If you guys take the security class at some other time, you'll learn all about those concepts. Okay? All right. We're almost finished with this section here. I want to push through. We normally take our break around 2:30 anyway, so we should be able to push through this in the next 15 minutes. And then I'll give you guys your afternoon break. Okay? Now, why is this significantly important? If I look at this diagram here, if this PC is talking to the web server out here, it's going to ARP for the MAC address of the gateway. If there are 1,000 computers out here that this PC is talking to, it's still going to ARP for the gateway. Well, it won't have to ARP anymore because it knows it. We don't do ARP every single time. We store that information. So the only entries that go in my database, my cache, what we call an ARP cache, the only entries that are uniquely identified in that cache are the ones inside my subnet. Everything outside of my subnet, there's just one entry. 10.1.1.1 is mapped to 3333. That's the gateway. The gateway IP and the gateway map. That's why when you look at your ARP cache on your computer, it probably doesn't have thousands and thousands of entries because most of the communication that you have is beyond your subnet. Now, if you are communicating to a lot of hosts inside your subnet, you would have individual entries for that. Routers do ARP as well. I mean, routers have to talk to hosts, so they're going to do ARP requests. They're going to put entries in the table. Here's one for .1, here's one for .2. These are the individual MAC addresses. Here's a little trick, though. Fast Ethernet 00. We can see that we've learned about all these hosts on Fast Ethernet 00. So if I was to kind of match this up with this diagram, let's say that this is Fast Ethernet 00. That router learned about all those hosts on that interface. So there's a bunch of hosts connected to the switch that the router talked to. Okay? But I know that the MAC address for Fast Ethernet 00, I know that it is 000A F434 9200. Okay? And I know that the IP address on the Fast Ethernet interface is 100.1. How do I know that? Here's how. This dash. In a router, that dash means that that is a local address. Anything with an H is something I learned from somebody else. Anything with a dash is a MAC address tied to that specific interface. Just a little tidbit of information.
And what does it mean by the type ARPA?
ARPA is Ethernet 2.
Ethernet 2?
Yeah, that's how it's defined in a Cisco router. Ethernet 2 encapsulation is ARPA. All right? Here is what we would see in our host. In our host, we would use the ARP-A command. I can see that I have a bunch of static entries here because computers generally participate in a lot of different types of networks, multicast networks and so on. But there was one entry that I learned dynamically. 172.20.100.1 mapped over to the 2C4138426751 address. This information is cached, which means it's stored temporarily. The amount of time it's stored depends on the device, but we don't ARP every single time we have to send a frame. If I know the MAC address, if I have an entry in my table, I just simply use that cache to build my frame. I don't try and discover. All right? Oh, something happened. I went back all the way to slide number 4. I don't think we want to start all over again. Let me pause the recording. All right, sorry about that. We got mixed up there a little bit with our slides, but we're back on schedule here. So the last thing that we're going to talk about in this section here is switching. And we're going to talk about how switches function. It's a very, very simple concept. It's not that difficult. All right, we know already that switches operate at layer 2 of our OSI model, right? Now, switches also create these things called separate collision domains. In other words, every interface on a switch is its own collision domain. And technically, there really shouldn't even be collisions because most switches operate in something called full duplex communication. What does that mean, full duplex communication? That means that I can send information on the wire the same time I'm receiving information. All right? And that's because we have different transmit and receive pairs. So I can send data to you while you're sending data to me. That doesn't cause a collision. All right? We have high-speed ports. We have fast internal switching processes in Cisco devices. We use these things called ASICs, or application-specific integrated circuits, that allow us to do pretty much wire speed switching, right? Very low cost per port, et cetera, et cetera. Not all switches are the same, by the way. You know, a lot of our customers, we have to convince them to spend $1,500 on a switch instead of going to Walmart and buying a $20 switch. Because first of all, the $20 switches are not manageable. You can't set up spanning tree, you can't set up VLANs, you can't do that kind of thing. But at the same time, the hardware in those $20 switches is so insufficient, right? Cisco switches have very large frame buffers so they can store lots of information. They have a lot of intelligence built into them and a lot of functionality. So there is a difference between a Dell switch and a Cisco switch. Dell switches fundamentally function the same, but they don't have the hardware in them to operate at the same wire speeds as a Cisco switch does. All right? Not to say that other people don't make good switches. They do, but Cisco is clearly the market leader in that space at least. A collision domain. We already talked about what the concept of a collision domain is, didn't we? Isn't it basically where devices have to compete to communicate? All ports in a hub belong to the same collision domain. So this is a 1, 2, 3, 4, 5, 6, 7, 8, 9 port device. If I had 9 hosts connected to this device, they would be competing for bandwidth. Microsegmentation is the concept of replacing hubs with switches. And when you do that, every interface becomes its own collision domain. Here we have one single collision domain. Here we have 3 separate collision domains because we have 3 ports. Still a single broadcast domain. Still a single broadcast domain, but separate collision domains. All right, we have a question from Giovanni. from Italy. The question is, how do you convince them to invest when they don't want to? Well, that's layer 8 and layer 9, right? It's very difficult. It is difficult because switching has become somewhat of a commodity, right? And we know that Cisco switches are very expensive. I mean, some of the switches that we installed in this facility were $8,000 each, right? For 48 ports, where you can go and get a Dell 48-port switch for a few $100s. And it's really hard to convince somebody that, particularly a company, to spend the money on a Cisco switch. They don't know what buffers are. They don't know what cut-through switching is. They don't know what 802.1x is and all these other things. So it's tough. It's tough. And sometimes it's not necessary. Some customers don't need $5,000 switches because they're not running things like VLANs. They're not running 802.1x. They're not running QoS or enhanced QoS, right? So a lot of the times, to answer your question, Giovanni, a lot of the times the need is driven by the customer's need to manage their data. And simply saying, look, if you want to implement QoS, you need this switch. If you want to implement Power over Ethernet, you need this switch. If you want to implement stacking or stack-wise technology, you need this switch. Redundant power, you need this switch, and so on. Okay? It's not easy, trust me. All right? Now, broadcast domains. We already know that a broadcast domain is essentially the extent of where a packet goes or a frame goes if it's a broadcast. Switches do not filter broadcasts. Hubs do not filter broadcasts. Whether they're layer 2 or layer 3, it doesn't matter. So switches do not break up broadcast domains. Hubs do not break up broadcast domains. But a broadcast will never, ever go through a router. Ever. There is no exception to that rule. You cannot send a broadcast through a router, period. Okay? For that reason, it is said that routers break up broadcast domains. Every interface on a router is its own broadcast domain. All right, we already talked about this concept of half duplex and full duplex. Half duplex means you can send at one time, or you can receive at one time, but you can't do both. Can't send and receive at the same time. Okay? Full duplex, you can send and receive at the same time. All right? And most of our modern technology, switching technology, is full duplex. The last thing we'll talk about in this section, just a couple of slides on switching. Okay, we already know that a layer 2 switch, oh, we got another question. Zaid, it says, what's the difference between simplex and half duplex? Nothing. Those terms are synonymous. All right? Well, simplex generally means communication only goes in one direction, always. Whereas half duplex means you can communicate in both directions, but not at the same time. Okay? But essentially, logically, it means the same thing. Another question, is it not so that a layer 3 switch can also break broadcast domains? I'm guessing he meant, is it not true? Yes. Actually, layer 3 switches have a routing function. So when routing is involved, broadcasts don't get forwarded. VLANs, which we'll talk about in a couple of days, virtual local area networks, break up broadcast domains. But not because they're VLANs, but because the only way you can get from one VLAN to another is through a router or a routing function. So it all boils down to routing. Routers separate broadcast domains. Okay? Layer 2 switches connect end devices to a central intermediate device. They perform switching and filtering based on MAC address. Okay? In fact, a switch builds a database called a MAC address table. That MAC address table is built dynamically in the switch, and that MAC address table is used to make forwarding decisions. So out of the box, you turn on a switch, it's dumb as a brick. It doesn't know anything. So out of the box, a switch acts like a hub. But as data flows through that switch, as frames go back and forth through the switch starts to learn things. It learns about who's attached to what port, who's connected where, and it starts to build a database called a MAC address table. That database is what's used by the switch to make its forwarding decisions. Okay? So as I said, a switch has to first learn what devices exist on what ports before it can transmit effectively. Okay? James Roma says he can't hear. Can everybody else hear me okay? Did I lose my audio? Pedro says he can hear. All right. All right. You had a question, sir.
Yes, if one of the ports, the device of it changed, does a Cisco switch make like a refreshment or update for the MAC address database?
Okay, so the question was, in case you guys didn't hear it online, is if a device changes its position, right? It moves around on the network or something like that, or if it goes away, does the switch update? Okay? I'm going to answer that question, and then I'm going to describe in detail more to answer your question even further. But switches are passive devices. That means to say that a switch doesn't actively go try to find out who's connected where. It simply waits for data to flow back and forth. If data doesn't flow for a while, then the switch assumes that that device doesn't exist anymore, and it deletes that entry from the database. Or if the switch sees that device from another port, then it updates its database, but only after traffic flows through the switch. So to answer your question, yes, the switch updates its information, but not in a proactive way. It's passive. Switches are very, very passive devices. They do not dynamically try to go down and look at each port and say, okay, who's connected to this port? Who's connected to this port? They simply wait for data to flow through the network. All right, now we have another question. Port security shuts down that port. Oh, yeah. If you have port security configured, which we will be talking about, by the way, in a couple of days, port security. Okay? Now, I don't know if I completely answered your question, but after we go through the next two slides, you'll be very clear about it. All right? Switches have to learn what devices exist on what ports before they can transmit frames effectively. Okay? It builds a table called a MAC address table, which goes into something called content addressable memory. Okay? Basically what the switch is doing is it's mapping a port to a MAC address. So MAC address A learned on port 1. MAC address B learned on port 2, and so on. Now, Pedro says, what about MAC address spoofing? Let's say I spoof the MAC address of my device to a device that already exists in the switch. Would the frame then be sent to both devices? The answer is no. What's going to happen is the switch will rewrite its database to wherever the location is. And each time it hears a frame from the devices that have the same MAC, it keeps switching where that MAC address exists. In other words, the MAC address doesn't get written to two separate ports. Does that make sense? It'll go back and forth, but it won't be written to two separate ports. Okay? CAM is MAC backwards, but that's not what it means. It's just content addressable memory. Just think of it as like RAM. It's storage location. The information that's stored in the MAC address is what we use to send our frames. All right, so if a switch receives a frame with a destination MAC address that's not in the table, a switch receives a frame with a destination MAC not in the table, what is the switch going to do with that frame? The switch has no idea where that frame is supposed to go, so it's going to flood it out of every port except for the port it came in. Remember what I said? Switches initially are kind of dumb devices. They don't understand where everybody is, so they'll flood their information. But as they start to see frames going back and forth, back and forth, back and forth, they're going to start learning. They're going to start learning information. Okay? All right. Let's see a visual representation of that, and then we'll wrap up this chapter. PC1 is connected to a 2950 on port 1. It wants to talk to PC2 on port 3. Okay? Let's say it's an ARP request coming from PC1. The ARP request is a broadcast, but the source of that frame is PC1. So as soon as that frame arrives on port 1, what does the switch do? The first thing it does is it adds PC1's MAC address to the database, as you can see on the right side there. Adds PC1's MAC address to the database, and it says, okay, 9B40 is on port 1. The destination address is a broadcast, which means it doesn't exist in the table. So what does the switch do with the frame? It floods it out of every port except for the port it came in on, which means it goes out of port 2, it goes out of port 3. PC2 is going to receive that frame. It's going to respond with a frame back to PC1. What's the first thing the switch is going to do? It's going to add PC2 to the database, saying, okay, MAC 0440 is on port 3. Now, is it going to flood the response, or is it going to switch the response? It's going to switch the response. Why? Because PC1's MAC address is in the table. The more active the switch becomes, in other words, the more frames that pass through the switch, the more the switch learns, and the more efficient that switch becomes. Okay? As long as the switch has an entry in its database, it is going to forward that frame out of that port only. If the entry does not exist in the database for a destination, it will flood the frame out of every port except for the port it came in on. By the way, this is not just a Cisco thing. Every switch operates this way. Even the off-the-shelf switches operate this way. Is it possible to have more than one MAC address on a port?
Yes.
Yes. Because what if I have, say, a downstream switch? Excuse me, here I have a downstream switch. Maybe I have 20 or 30 hosts connected here. Excuse me. If those 20 or 30 hosts are talking to this PC, they're all going to be learned on the same port, right? The MAC address table is locally significant to that switch. So it is possible to have more than one MAC address on a port if you have a device that allows more than one device to be connected to that port. Okay? All right, one last concept before we wrap up here, stacking. Now we've added this to our repertoire here. We've added this to our discussion because it's actually covered on the exam, the stacking concept. Stackwise, which is not it's just a marketing term or the name that Cisco uses to define their stacking functions, is a way for us to collectively utilize or combine the resources of our switches together to provide for redundancy, but also to make the switches look like they're a single switch, right? We're basically taking these stackable switches and we're making them look like a chassis. Now these happen to be higher end switches, and we'll talk about what these cables on the back represent. 3850s, that's what I was looking for. Do the switch ports have their own MAC address? Yes. Dan, question. Every switch has a base MAC address. And you can see that base MAC address by typing show version. But every port on a switch has its own unique MAC address as well. That's why Cisco has so many OUIs, because they make a lot of switches. Okay? Now what you're seeing on the left here, well, on the left side facing the back here, this is the stack-wise cable, and this is what we call power stacking. So these switches are capable of becoming effectively one switch. That cable is a proprietary cable, right? A physical layer, not data link layer. It is a 32 gigabit per second backplane. We don't call it trunking per se because it's a physical layer concept. It's not a data link layer concept. Trunks and VLANs, those are layer 2 concepts. This is literally a physical layer channel, or it's a bus. So by stacking cables or stacking switches together, when you go into the command line for the switch, it looks like one switch. So if this is the master switch in the stack, and these guys are my secondary switches, when I telnet, if I have an IP address that's assigned to an SVI on the switch, when I go in, I'm configuring all 4 of the switches. In fact, the numbering for the ports changes. This might be switch 1 in the stack, this might be switch 2 in the stack, this might be switch 3 in the stack, and so on. So the interface numbers for the first switch might be 1/0/X, and the interfaces in the last switch in the stack might be 4/0/X. All right? Now the order of how those show up depends on the priority of the switches in the stack and how you provision the switches in the stack. All right? In Cisco, the 3700 and 3800 series switches, you can stack up to 9 switches together. Now, the other thing that you see here is something called the power stack. Cisco also made it possible to stack your power. So if the power supplies, both power supplies in this switch fail, it can draw power from the other power supplies in the stack. So it gives you kind of that full redundancy. Okay? You'll also notice that the stack is a ring. It is a ring. So I go from port 1 down to port 2. I go from port 1 to 2, 1 to 2, 1 to 2. So if this switch fails, the second switch in the stack fails, we still have connectivity because we have half of a ring left over. Now our speed is going to change from 32 gigs to 16 gigs, but at least we still have that connectivity. All right? Obviously here we get more port density and we get to pool resources. There's some stacking management that takes place, so it's not that we free up every resource. We still have some additional resources to make this function, but it's a pretty cool technology. Now for you guys online and anybody trying to build a home lab, there's a switch that's readily available on the used market for about $70 to $100 that has this technology built into it. It's called 3750. And you can get those 3750s online for pretty cheap. Very, very powerful switches. They were very, very expensive when they were new. And they have layer 3 functionality. They have stacking functionality. Those are generally the switches that I recommend to students to get for their lab environment because they do IPv6, they do IP, they do routing, stacking, they do everything that you need for a pretty small price. You know, you get the 2950s and the 3550 switches, they're going to be very limited. Even though they're cheap, 20 bucks or 15 bucks for a switch, they're very, very old. So they don't do a lot of the new stuff that you want to do. Okay? All right, that is the end of that chapter. So we are going to take our break. We're about 11 minutes behind schedule, but we'll go ahead and take our 15-minute break. and then we'll get into the next chapter. We're going to be doing some Cisco iOS stuff in the next chapter.